Hi, today in this video we'll talk about standard normal distribution. That what exactly is a standard normal distribution, what is a standard normal random variable, and how to find probabilities for a standard normal random variable. In our later videos, we'll talk about how exactly do we use standard normal distribution to find probabilities for a normal random variable. So let's start. First of all, what exactly is a standard normal variable? If z is a normally distributed random variable with mean mu is equal to 0 and standard deviation sigma is equal to 1, then z is called the standard normal variable or has a standard normal distribution. So what we are saying let's suppose z is a normally distributed random variable with mean is equal to 0 and standard deviation is equal to 1. That is any normally distributed random variable. It can be any normally distributed random variable which is satisfying two properties, that is mean is equal to 0 and standard deviation is equal to 1 is the standard normal variable, right? So basically can we say standard normal variable is a particular case of a normally distributed random variable, right? So standard normal random variable is just a particular case of a normally distributed random variable. And any variable that is a standard normal variable will follow a standard normal distribution, right? So thus the density function of the standard normal variable z is given by f of z is equal to 1 upon square root of 2 pi e to the power minus z square by 2, where z lies between minus infinity and infinity. Now let's see from where exactly this density function turned up. So let's suppose x is a normally distributed random variable. Right? So what is the density function for x over here? We all know f of x is equal to 1 upon sigma square root of 2 pi e to the power minus 1 by 2 x minus mu upon sigma whole square, where x lies between minus infinity and infinity, right? So we all know this is the density function from our previous videos also. Now we know for a standard normal distribution, all we need is that a normally distributed random variable has mean is equal to 0 and standard deviation is equal to 1, right? So now let's just put these figures in it. So can we say from this implies f of x is equal to 1 upon 1 square root of 2 pi e to the power minus 1 by 2 x minus 0 by 1 square. So wherein x lies between infinity and minus infinity, right? So can we say this simply implies f of x is equal to 1 upon square root of 2 pi e to the power minus half x square. Can we say this? So where x lies between infinity and minus infinity. So can we say this is same as this, right? Let me just mark it with a different color for you to understand it better. Can we say this is same as this? So from here we derive this density function that for any normally distributed random variable with mean equal to 0 and standard deviation equal to 1 is a standard normal variable with a standard normal distribution. Now here we will talk about area under the standard normal curve. So first of all, we all know, let's just write out the density function for a standard normal curve. Can we say f of z is equal to 1 upon square root of 2 pi e to the power minus z square by 2. This is something we have already seen, right? Where z lies between minus infinity and infinity. So we all know, let's first just simply sketch out a curve. So we all know any normal curve is like something like this, where it is centered around its mean mu, right? And is symmetric around its mean. This represents the f of x, infinity, and this is minus infinity, right? So can we say that since it's a standard normal curve and mean is equal to 0, so it's centered around 0, right? And this represents our density function and this represents our curve, right? Now, we all know this part. So let's suppose for any z greater than 0, I'll just let you know why we are taking z greater than 0 in a minute, but let's first start. if we define capital F of Z is equal to 0 to Z f of t dt. So why did we take this as basically greater than 0? Simply because our lower limit is 0. So it cannot be less than 0. The upper limit has to be greater than the lower limit. So we are taking it from 0 to Z f of t dt. Right? So if we want to represent it, can we say it is 1 upon square root of 2 pi integrating it under the limit 0 to Z e to the power minus half t square dt. Can we say this is true? Now, what we have done is we have simply integrated the density function between 0 to Z. So, can we say if I am integrating it from 0 to Z, can I say this is nothing other than the area under the standard normal curve where Z lies between Z is equal to 0 and Z is equal to small z. Is this true? We are simply saying f of z when we are integrating that density function. We are simply saying we are integrating the values of the probabilities that z lies between 0 to z, right? And since this is a curve, so if this is 0 and let's suppose this is the point z, can we say that this area is being represented by this capital F of z, right? We are saying this f of z represents the area under the standard normal curve between where z lies between 0 and z. Why? Because this f of x is our density function which is giving us probabilities, right? So we all know that the area under the standard normal curve represents the probability. So this is also the probability. If I want to find, let's suppose if I want to find probability that z lies between z is equal to z and z is equal to z, can I say this is simply nothing other than this f of z? So basically this f of z represents the area under the standard normal curve and the probability that f of z is equal to that probability that f of z represents the probability that z lies between 0 and z, right? Now you must be thinking that in order to find all these probabilities, let's suppose that is probability that z lies between 0 and z is equal to f of z, right? So this is what we have seen, right? So you must be thinking in order to like calculate these probabilities, you would have to integrate the function every time, right? But no, we don't have to do it. Why? Because we have some like given tables where these values have already been evaluated for us. So we won't have to, just find these, like we won't have to integrate and everything all together. We have tables to do that and we'll see how. So let's suppose I need to find the probability that z lies between 0 and 2.27. Like this is the interval. So basically I just need to find a z function. After this, if I have to find these probabilities, instead of integrating, I have a given table which I can directly use in your exams, right? These table will be given to you. You don't have to by heart these values at all, right? So if I want to find the probability that z lies between 0 and 2.27, how do we find it? Let's see. So just look at this part, this region. All you need to do is this 2.27, can I say it is 2.20 plus 0.07? Can we say this? Right? 2.27 is nothing other than 2.20 plus 0.07. So what we will do is from this region, from over here, we will simply find 2.2. This is our 2.2. Okay, let's just mark it as 2.2 as this. Now, and next part is 0.07. So here we mark it as this. So what does this come up? This comes up to be probability the probability that 0 lies between z lies between 0 and 2.27 is equal to 0.4884. So what did we do is, we simply took, whatever value is like before the decimal, we took that value, and one place after the decimal, we took out from over here where we have different rows, and the second place after the decimal, like the second place after the decimal, we took that in our column. So from over there we took the 0.07, and from here we took this 2.2. Now let's suppose if I ask you to find a probability that z lies between, let's suppose 1.23. How will you find? So we know 1.23 is equal to 1.20 plus 0.03, or we know that one place after the decimal is still 1.2. So 1.2 will take at one part and 3 as another. So 1.2 will check in the rows, which is over here 1.2. We'll simply mark it like this, 1.2, and then we have a 0.03. 0.03 we will see over here. So the 0.03 is still here. So can we say this is equal to 0.3907? So we are taking this value, right? We have simply taken from here 1.2 from here and 0.03 from here in order to find the probability that lies between 0 and 1.23. Fine. So this is how we basically use the standard normal table in order to find the standard normal probabilities. Now we'll see a few properties of the standard normal distribution and then directly move on to the questions where we will have multiple practice of how to find the standard normal probabilities from the given table. Let's see. Now, we will see a few important points which are very, very important from your examination point of view as well. First is, if x is a continuous random variable, then probability that x lies between a and b is equal to probability that x is greater than equal to a and less than b is equal to probability that x is greater than a less than equal to b is equal to the probability that x is greater than equal to a and less than equal to b. Right? One. Second, probability that x is less than a is equal to probability x is less than equal to a, and probability x is greater than a is equal to probability x is greater than equal to a. Right? So what we are saying is, if x is a continuous random variable, then the probabilities that x lies in some interval is not affected by whether or not either of the endpoints of the intervals are included or excluded. It does not matter whether these endpoints are included or excluded. This equal to does not matter. Why? See, first of all, we all know that probability for a continuous random variable is always equal to 0. So probability that x is equal to a is always equal to 0 because it's a point probability. For continuous distribution, we always find the interval probabilities, right? So this is same. So even if you put this equal to, it does not matter. So probability x is less than a is equal to probability that x is less than equal to a, and probability that x is greater than a is same as the probability that x is greater than equal to a, because probabilities or the point probabilities are always 0 for a continuous random variable, right? Next property says probability that z lies between minus infinity and 0 is equal to probability that z lies between 0 and infinity, which is equal to 0.5, right? So first of all, we know if this is our standard normal curve and standard normal curve is centered around mean, that is equal to 0. In that case, we all know that the total area under this curve is equal to 1, right? So probability that z lies between infinity and minus infinity is always equal to 1. We all know this. And this ordinate, that is mean is equal to 0, divides this entire curve into two equal parts, right? This we already know that mean always divides the curve into two equal parts. that is left part is equal to the right part. And since these are same and the sum is equal to 1, can I say the probability, so from here, let me write, can I say from here that the probability that z is less than 0 is equal to 0.5, and probability that z is greater than 0 is equal to 0.5. Why? Because it's dividing the curve into two equal parts, right? And since it's dividing the curve into two equal parts, that is at 0, so these two parts are equal. So this represents the probability that z is less than 0, and this represents the probability that z is greater than 0. And z less than 0 means probability that z lies between 0 and minus infinity. And this means that z greater than 0 simply means the probability that z lies between infinity and 0, right? And thus this is equal to 0.5, right? Okay, now third, we all know, let's we just draw the curve again. We all know that this curve is symmetric around mean mu is equal to 0, right? It is a symmetric. Why? Because it's a normal curve, and any normal curve is symmetric around its mean. And over here mean is 0, so it's basically it's symmetric around 0 also. Okay, so now what we are saying is, let's suppose there are two values. One is, let's suppose one is minus a and second is a. What does this mean? If a, let's suppose if a is 1, then minus a means minus 1, right? So we know since the curve is symmetric, so can we say this area is equal to this area? Yes or no? Right? We can say that since it's symmetric around mean equal to 0, so this area is equal to this area. So from here can we say probability that z lies between minus a and 0, that is this area, is same as the probability that z lies between a and 0, which is this area, right? So what do we say exactly? From where did this turn up? This turned up simply by symmetry. This we found simply by symmetry, right? Now these are very important 3 points. Let's see again that the point probabilities are always 0. Second, that mean or 0 divides this curve into two equal parts. And third, by the rule of symmetry, probability that z lies between minus a and 0 is same as the probability that z lies between 0 and a. So basically, all we need to just keep these three properties in mind in order to solve the question, and it will become very easier to do now. So now let's see. Okay, so first of all, this question has been taken from Taxman's Fundamentals of Business Statistics by Dr. J.K. Thukral. So this is the 4th edition, and this question that we have taken is directly from there, right? So let's start. Find the area under the standard normal curve, which lies to the right of z is equal to 2.7. So whenever we are solving the question, to make it easier, all we will do is we'll simply sketch the curve first. So let's just sketch the curve. This is this, and mu is equal to 0, and this is our f of z, right? Okay, this is infinity and this is minus infinity. To the right of z is equal to 2.7. First of all, let's mark this z. Z is equal to 2.7. We need towards the right, so we need this area, right? So let me just write it. First part is to the right of z is equal to 2.7. So marking this area, can we say this is nothing other than probability that z is greater than 2.7? Just evaluate it. Can we say this is nothing other than the probability that z is greater than 2.7? Right? Now we need to find it. How will we find it? See, first of all, in order to find this, all we know is that the probability that z lies between 0 and 2.7 plus the probability that z is greater than 2.7 is equal to 0.5, right? We know the total area towards the right of 0 is 0.5, right, from here. Right? So total area towards the right of here is 0.5. So we now, in order to find this probability z is greater than 2.7, can we say it is nothing other than 0.5 minus probability that z lies between 0 and 2.7, right? So this is nothing other than 0.5 minus probability z lies between 0 and 2.7. How will you find? See, we'll see in this rows part 2.7, and since the second decimal place is 0, so this is 2.7 means this area 0.4965, right? So from here what we can say, this is equal to 0.0035, right? So this is how we find the area towards the right of 0.27. Z equal to Z is equal to 2.7. Now, part number 2. So our second part was to the left of Z is equal to 1.73. So let's sketch it again. See, over here also it's marked that this is this area lying between 0 and Z, right? Okay, so let's just mark it to the left of Z is equal to 1.73. So see, this is very important that first of all you will mark this mu is equal to 0. This is very important. That will make it easier. So Z is equal to 1.73 to the left. To the left means this area. So probability that Z is less than 1.73, right? So this is so simple. We all know that this area towards the left of 0 is 0.5. We have seen in the property, plus the probabilities that Z lies between 0 and 1.73, right? So basically this region plus this region will give us the probabilities. So this is 0.5 plus probability 0 and 1.73. So how will we see it? 0 and 1.73. 1.73 means in the rows part we'll see 1.7, which is here, and then 0.03. So let's just mark this row, and 0.03 is here. So can we say this is this value? For you it's easier. So this is 0.5 plus 0.4582. So this is 0.9582, right? All right. Now third question is to the right of Z is equal to minus 0.66. So let's draw it to the right. Mu is equal to 0. This is minus 0.66 to the right. So we need this entire region. So can we say this is equal to probability that Z is greater than minus 0.66 is equal to probability that Z lies between minus 0.66 and 0 plus the probability that Z is greater than 0, right? So by symmetry, we know that this is equal to 0.5. So can we say that probability Z is greater than minus 0.66? We know this, and also by symmetry, we all know that Z lies between 0 and minus 0.66 is same as probability that Z lies between 0 and 0.66. Right? We have already seen over here in this property by the symmetry rule. So from here 0.66 means 0.6 is over here, and first place of decimal is 0.6 and another is also 6. So from here, so this becomes 0.2454. 0.2454 plus 0.5, and this is equal to 0.9. Sorry, this becomes 0.745. 0.7454, right? Okay. Now fourth part. Fourth part is to the left of z is equal to minus 1.88. So to the left of this means, let's again mark it, mu is equal to 0, minus 1.88 is here. To the left, left means this region, yes or no, right? So if we want to find the probability that z is less than minus 1.88, can I say this is simply, in order to find this, can I say this is equal to 0.5 minus the probability that z lies between minus 1.88. Now let me just rewrite it. This is equal to 0.5 minus probability that z lies between minus 1.88 and 0, right? Why did it write it? Because total area to the left of mean is 0.5. Is this true? Right? So thus from here, can we say this is equal to probability that z is less than minus 1.88 is equal to 0.5 minus, and this probability is equal to z lies between 0 and 1.88 by symmetry. So this is equal to 0.5 minus, now the probability z lies between 1.0 and 1.88 is simply 1.8 from here, and 1.88 means this. So this is the point, that is 0.4699. What does this become? This becomes simply 0.0301, right? Okay. So fifth part, we need to find the probability that z lies between 1.25 and 1.67. So let's again draw the curve. This is the curve, right? Mu is equal to 0. This is 1.25 and this is 1.67. So how do we find it? Can I say in this, all we need to do is, I'll find this probability that z lies between 1.67 and 0 minus this area, probability that z lies between 0 and 1.25. Can I say, if I minus this, so what will I get? I'll get this region that we are demanding, right? So we just simply need to subtract the two probabilities. So let's do probabilities that z lie between 0 and 1.67. 1.67 means 1.6 from here and 0.07 is from here. So this is 0.4525 minus probability that lies between 0 and 1.25 is 1.2 is from here and 0.05 is from here, 0.3944. So this becomes 0.0581, right? So now in order to find the probability between minus 1.85 minus 0.9 is, let's just mark the 2 points. This is minus 0.9 and this portion is minus 1.85. So again, this region we need to find. So again, can we do the similar work? This bigger region, right, minus this region. If we subtract this small blue region from this green region, will we get this red region, right? So this is nothing other than probability that z lies between minus 1.85 and 0 minus the probability that z lies between 0 and minus 0.9, right? So by symmetry, can I say this is equal to the probability that Z lies between 0 and 1.85 minus probability that Z lies between 0.9 and 0. Right? So now we just simply need to look at the table for this. 0 and 1.85. 1.85 is here. This is our 1.85. So this is 0.4678 minus probability 0 and 0.9 is from here, 0 and 0.9, which is this 0.3159. So this becomes 0.1519, right? Okay, last question. The probability that Z lies between minus 1.45 and 1.45. Now this, by now everyone must know, right? So by law of symmetry, this area and this area is same, right? So can I say this is equal to the probability that Z lies between minus 1.45 and 0 plus the probability that Z lies between 0 and 1.45, right? And by law of symmetry, these two are equal. So this is 2 into probability that Z lies between 0 and 1.45. So this is equal to 2 into what is the probability that Z lies between 0 and 1.45. Again from the table over here, 1.4 is over here and 0.05 is here. This part is 0.4265. 0.4265. So this gives us the value of 0.853, right? So this is how exactly we find the probabilities for a standard normal table using a standard normal table. Now in our later videos, we'll talk about how to find probabilities or how to use these probabilities in order to find probabilities for a normal distribution. I hope you like this video. Do subscribe this channel for more videos. Thank you.